Okay, let's get started. This is the truest sense of night class. Who's ready for 3:55 at this late at night?
Yeah.
Yeah, woo! All right, so as you might have guessed, I'm Ryan.e.dougherty. I'm technically a professor now at a different university, hence by my shirt, so you can actually call me professor, but just if you don't want to bother with that, just call me Ryan. We obviously meet here. Office hours are Wednesdays, 5 to 7, in Brickyard on the 4th floor. So if you have any questions or can't resolve something over email or want to dispute grades, that would be the place to do it. The textbook, I'm sure you can find it online pretty easily, but it's absolutely not required. You do not have to buy it. It's horrendously expensive, I know, because I have a copy. I know it's expensive. Don't get it if you don't actually need it. I'm gonna follow the text pretty closely, so you can just watch the videos or come to class. It's pretty much getting the same thing anyway. Plus, there's some more stuff in the SIPSR book that we're not gonna cover, so you may be confused. Are we actually doing this or doing this or not doing this? So you don't actually need it. So the prereqs are 310. So hopefully you've taken that. Actually, you should have because you couldn't register without it. But 310, you're not actually going to use a lot of material from. But 243, we're going to use a load of material from. So if you're not up to speed on 243, on discrete math stuff, first off, get acquainted with it. But if you're not sure what parts of discrete math are we going to cover or not cover or require, Chapter 0 of the SIPSR book has all of the discrete math that you need. So there are some things that you may have taken in 243 that we're not actually going to use. Chapter 0 is your friend here. So if you don't know what a power set is or what a relation is, or if any of these terms sound unfamiliar to you, go to Chapter 0 of SIPSR. It will definitely help you. Yeah, so my email's here. And our TA this semester will be Varun. He's actually a good friend of mine. He was on a project once we did a long time ago. So he'll be great. What he'll be doing is helping me proctor, but more importantly, he's going to put up each week, not this week, but every week after, he's going to put up recitations. He's going to make a video on recitations, going over some problems and working through solutions. So basically practice problems for that. Any questions about logistics stuff? Okay, so what's the class about? So the class is really, oh yeah, go ahead.
So on your syllabus website that you said that it's our responsibility to like find or the rest of the class. Where will the you said that there was a solution. When will those like articles or whatever he does in the class? When will it be posted?
So when things will be posted on the webpage. Yeah, so everything will be posted on the webpage. Yeah. So I actually just put up the lecture video playlist, the YouTube link, and I'm going to put all of so the things that I'm going to be drawing on here, they're going to be saved as PDFs. I'm going to upload them to the page. Yep. Other questions about logistics type things? Yeah.
How do you want us to turn around?
So I'm going to go over that. Yeah. Other questions? Okay. So what's the class about? I would actually argue that this is probably the most important class you'll ever take. So why is that the case? So the short answer is it's really getting to the core of what a computer scientist actually is. So I'm guessing most of you are computer scientists, but it's getting to the core of what it actually means to be a computer scientist. What does it mean to actually compute something? Are there problems that your computer can't solve? Raise your hand if you think there's a problem that your computer can't solve. Given any amount of time. So given as much time as you want, as much resources as you want, are there problems that your computer cluster can't solve? It turns out there are a lot of problems. In fact, the vast majority of them are not solvable by any computer. So if your boss comes to you and says, oh, I want you to solve this problem for me. So one example would be, so on my computer at home, I do researchy things. And there's a program I have running on my computer that's hitting the 8-week mark right now. It's been running for 8 weeks. And I know it's going to stop. But if you're looking at that program run, how do you know it's going to stop? Anyone have any idea? Yeah. What's that? A loading bar. It's actually not going to print anything until the very end. So there's actually no indication. So what if your boss asks you, okay, we're going to provide software as a service to figure out whether a user submits a program, and we're going to determine for them whether it's going to run an infinite loop, or so basically it's going to run for an infinitely long time, or it's going to stop at some point. Sound pretty simple? And we're going to sell it to Google and make billions of dollars. Do you think there's a reason why it hasn't been done? Because that problem is not possible by any computer. There is no way to be able to take an arbitrary program in and figure out whether it's going to run forever or not. Isn't that amazing? That something that is so simple to state and understand is actually impossible to do. And in fact, the vast majority of problems are unsolvable. And what's even more amazing about this is that just using a basic tool from 243, we can prove that right now, amazingly. So how many of you have seen the proof that there are more real numbers than natural numbers? You see why I'm saying go to chapter 0? Because that is something that we'll be using, okay? So there are more real numbers than natural numbers. And a natural consequence of that is that there are some problems that are unsolvable by computers, which is actually pretty amazing. But what we'll be doing is, instead of talking about this, a model for our computer, we're going to be talking about different kinds of models along the way. So we'll be talking about a very simple model that's way simpler than your computer, because we kind of also want to answer the question, for a given problem that we want to solve that is tractable, that our computer can solve, do we really need a full-fledged C++ program or Python program to do it? Or is there a much simpler way to do it? So those are the types of questions we'll be answering. So we'll be starting off at a very simple model and then saying, okay, we can prove some things about this model, solve some things using this model, and then we'll be able to show that there are some things you can't solve in that model. And then we'll add some more power onto it to make it more capable, but we'll actually be sacrificing some problems that we can solve with that model along the way. And then we'll find that that model can't solve everything, so we move up to a model for our computers, and then we finally end by saying, oh, there are some problems that our computer can't solve. So that's basically what the class is about, is understanding what does it mean to compute something. Do we really need all of this computation power, or can we work with a much simpler thing? So how many of you know what TCP/IP is? So basically the mechanism that all internet communications are based is based on the very simplest model that we'll be studying. So this very important model of computation is underpinned by this very simple model. What about your compiler? How is it implemented? Well, the vast majority of compilers are implemented with something called a context-free grammar, which is that middle model, not the simplest or the most complex. So something that can look at an arbitrary program and compile it down, you don't need a full C++ program to do that. You can just work with this simpler model, and it's a lot easier to work with. So it's understanding what types of computation you actually need to solve a problem. Any questions about what the class is about? Okay, class is over, dismissed. All right. Minus a few details. Okay, so that's the class description. Some major topics, basically the things we'll be covering most likely. I have to get through the first three, but the last 2 times I taught this, we got through the next 2, and then we may get to the 6th one if we need to, or if we can. So the reason why I talk about the last 2 instead of the first 3 is that how many of you heard of the P versus NP question? So things about, okay, talking about problems that a computer can solve, but I want to have the restriction that they run efficiently, they run quickly. What kinds of problems can I solve quickly? So that's the P versus NP type question. Okay, so someone asked about assessment type stuff. So the main things for assessment are basically come to class, please. So those 100 points should be super easy to get. And then we'll have 3 tests, 1 on the 6th, 1 on the 25th, and then 1 on the last day. So someone asked about homework submission. So the way that we're going to do this is you're going to, so on the course webpage, I have quote unquote due links for each of the homeworks. So what you'll be doing is, if you want to, because this is optional, you'll submit homeworks for feedback only. So you won't get like a grade or whatever, but you'll get feedback and say, oh, your proof is wrong because of this, or your submission could be a little better if you added this and this, or great job, this is exactly what we're expecting. So that type of things to help you along, because a numerical grade can be a little bit helpful sometimes, but feedback as to knowing exactly what you're doing wrong is much more helpful, I think. Because it's much better if you lose points 0 times versus losing points once. Okay? So the homework submissions are for you to turn in class, so it's a hard copy in class, and I'll shift those off to the grader, and then the grader will provide feedback, and I'll bring them back here, and then you'll be able to look at the feedback. So it's hard copy in class. So another thing, is there a Blackboard site for the class or Canvas? No, so should I expect an email about, is there a Blackboard or Canvas site in like a few weeks? Is there a Blackboard or Canvas site? Okay, there's no Blackboard or Canvas site. Okay, one more thing about assessment here. So I like to reward people who understand that they messed up at the beginning of the class and worked their tail off at the very end, because that shows growth and development. So what my policy is that the final exam is cumulative, but as to offload that, if you do better percentage-wise on the final, it replaces the lower percentage test. So if you got like, say, 60% on midterm 1 and got like a 80% on the final, then midterm 1 will be 80%. So it replaces old stuff because you're showing that you have learned things at the end of the class. Okay. Any questions about assessment? Yeah.
If both of your first 2 midterms are lower than hours, replace both.
Right. So it'll replace earlier tests independently. So it might replace 1 or 0 or both, depending on. So it's helping you as much as possible. Whatever it helps you the most there. Other questions about assessment? So do you think I recommend you doing the homework here? Yes, absolutely do the homework. The feedback is absolutely helpful here, okay? So absolutely do the homework. Okay, so some email policy. I always say that if you don't follow this, I don't answer, but then I answer them anyway. So this is just basically go to Piazza if it's not an individual question, essentially. So if you have like a general question, like you didn't understand something or whatever, just go to Piazza. The TA or I or one of your fellow classmates will answer it, and then we'll all benefit from that. If you have individual questions, obviously come to me or the TA, whoever is more relevant for the situation. Okay, grade appeals, just within a few days, so 3 days here, submit a written reason why you think you should get more points on something. I try to be as fair as I possibly can, give as much partial credit as I possibly can, but sometimes I just wholly screw up. So if you bring it to me, I can look at it. So just follow this policy and everything will be hunky-dory. Okay, so here's an important one. If you have something to do with DRC, any kind of accommodation type stuff, I'm absolutely willing to help you, but you have to let me know as soon as possible so I can make all of the appropriate arrangements. If you tell me like 1 hour before the test, whatever the test day is, to tell me that I need to send a test somewhere else, I probably am not going to answer that. Okay, so just tell me as soon as possible if you have a DRC type thing. Okay, any questions on administrative stuff? About any of that? Oh, I should have mentioned one thing. So the class is hour 45. So even I don't like listening to myself talk for an hour 45 straight. And I'm sure none of you will be wanting to listen to theoretical topics for, what is that? So that'll be 105 straight minutes. So what we're going to do is we're going to do 50 minutes, 5-minute break, 50 minutes, and then we'll let you out of here. Okay? The break is absolutely helpful, especially for me, because I have to talk a lot. Okay, my favorite section to talk about. You can tell by my sarcasm, it probably isn't. So this is probably not going to be an issue this semester because we don't have any homeworks that are worth anything. So for homeworks, because they're not graded, please work with each other on this with full solutions. Please do it. It's absolutely helpful. And even if you work with each other, you can still submit it because it's not going to count for anything. So don't worry about that. What I do worry about are the other two things. So for attendance and for midterm final exam stuff. So there is an academic policy that says that if there's an attendance sheet and you write your name on the attendance sheet and leave, that's an academic integrity violation. Okay? So what do I not want you to do? Do I want you to write your name and walk out? It's not a rhetorical question. Yes or no? No, do not do that. Okay? So, yeah. So if you are a person to do that, and I hope no one in here is like that, so it's a 0 on the day that it's issued and a third of a letter grade drop in addition. Okay? So it's not just a 0, it's a 0 plus a third of a letter grade drop. If you do something academic integrity type related on the midterms or the final, it's much worse. So if you'll get a 0 on the entire thing and a full letter grade drop in addition to that. So do you think it's a good idea to cheat on the final or the midterm exams? So for the tests, that's why I've made them open book. So all 3 tests are open book. No computers or anything, but like any written materials you have, anything you wish. Okay? So because I know it's this seems like a harsh policy, but I take academic integrity seriously. So I hope open book can help mitigate against that. Okay, any questions on integrity things? Yeah.
So like for attendance, if we sign in and have to leave 5 minutes later because of a family emergency, should we just email you and let you know?
Absolutely great question. So I hope all of you can ask great questions like that. So if you have like an emergency or something, just let me know. What usually happens with like emergencies, like you can't attend a class one day or can't attend a test or something, I just exempt you from the grade. So it's as if it never happened. And by exempt, I mean that everything else is uniformly scaled up so that it covers essentially whatever the thing is that you missed. Okay, so if you have an actual documented emergency, just send me the documentation, and I have no issue with giving exemptions with that. No problem at all. Because your mental health or your family's health is much more important than this class, I understand. I had a situation like that a long time ago, so I completely understand. Other questions about, yeah?
For open book, is it just written stuff, or can you have print it out?
You're really trying my patience. I'll say anything. But which one do you think I prefer, written or typed stuff? Written. Why?
Academic.
No, it's not. It's nothing to do with academic integrity because it's open book. I allow you anything.
If you write it, you remember it.
Exactly. If you write it, you remember it a lot better. So if you are to use something, I highly recommend you write it first because whenever I take a test and I write something down on my cheat sheet, I don't even use the cheat sheet because I already know the material at that point. So writing things is a lot better, but you can type things if you want. You can use the same notes as another classmate if you want, whatever notes that you wish. You can't communicate with each other during it, obviously, but you can use whatever notes you wish.
I was saying, like, if I had like a book like this for the notes in class, I could just bring this to the
Yeah.
exam.
Yeah, literally anything you want. So I actually, here's a funny story, so you know it's good. So the first time I taught this class, I had a one-page policy. So my policy was you can bring 1 page of notes, and I don't really care about the dimensions of the page or whatever, as long as it doesn't distract the person next to you. I have photographic evidence of this. So what the student brought was an entire scroll of notes. So literally 10 feet long and like 3 feet wide or something, and it was in tiny handwriting the whole way. I wish I could say what grade the person got, but it wasn't good. I'll say that. So yeah, bring anything you want. My policy is do not disturb the person next to you because they're trying to concentrate, and if you disrupt their concentration, that's not a good thing. Anything else about academic integrity? Okay, let's zoom away from that dark section. And these last 3 are basically, just to sum up, if you just follow the rules of the university, try to be respectful to your other classmates. If you feel like you're a person who's a victim of something that's terrible that's happened, please come to me or go to these links here. They are great resources for you if you're a person who is in that type of situation. It hasn't happened with me before, but it's just that it might happen. So, but feel free to come to me if you think it's happened to you. Okay, any questions on the syllabus? Yeah.
How is grading?
Grade distribution, that's a loaded question. So what is my job? It's a very open-ended question, I know. So what is my job? My job is to look at all 64 of you, maybe there are 64, I'm not sure, but 64 who are currently enrolled and say, for each of these people, I'm going to assign a letter grade to them based on the effort that they've made in the semester. Do you think that's a fair assessment of my job? So my job is to say, okay, there are some people who have earned an A+, there are some people who have earned an A, some people have earned an A-, and et cetera all the way down. So do you think I'm going to curve this class? I think curving should be illegal. Why do you think I'm saying that curving should be illegal? Banned in all 50 states, 200 countries, yeah, it should be made illegal, yeah.
Because you're more focused on yourself compared to the peers versus your actual learning.
That is true, that you're focused more on like on your peers versus yourself. So it's less of an individual thing and more of a group thing. But there's a more fundamental issue. How does so here's actually a good crash course on curving. So the way that curving works is that usually you'll have a bell curve like this. okay? And then at the peak, there's a peak of this distribution. That peak, if you're going to apply curving in a naive way, is the borderline between a B minus and a C plus. That's usually what happens. So what if this spike right here is at 95%? Do you think those people deserve a B minus or a C plus? No. So do you think I'm going to curve here? Or what if, say, like the highest score on anyone's work overall was 50%? Should that person get an A plus? Probably not. So what I try to do is I say, I'm going to look at the entire distribution and say, okay, where do you think is an A plus here? Where is an A here? Where is an A minus here? And I try to find natural breaks in the data. So if two people are extremely close to each other, I'm probably not going to put a separator in between them. But if there's like a 2 or 3% gap between a group of people, two groups of people, then I might put it there. So to really answer your question, usually it is, so you'll probably hate me after this, but it's 5% for each third of a letter grade. So A plus is 95 and up, A is 90 to 95, A minus is 85 to 90, B plus is 80 to 85, etc., all the way down. So why do you think I said you might hate me?
Oh, this is going to be a hard class.
Someone just realized it's going to be a hard class. This is a hard class. So the last time I taught this, what I set an A plus to be is 85 and up. Okay? So if I left it at 95, do you think everyone else is going to hate you? Probably. So I try to adjust based on how hard the class actually was. Sometimes it's easier, sometimes it's harder, and I actually do understand whether a class is harder or not via more students who can understand certain things, or going more to the TA, or not doing as well on the test. I understand when a class is harder or when it's easier. So I try to adjust when it's actually useful. But if I do see effort from some people, I do bump their grade up. So it's not, I don't just look at the raw total and just say automatic B plus no matter what, and just take a blind eye to everything that they did. So there's actually one example last semester, because this person showed so much work throughout the entire semester, from their raw total, they got a full letter grade raise from what they had, because they showed they actually did work very hard, much more than anyone else combined, okay? So I do understand that some people work harder than others. I want you all to work hard. I want you to learn this material and love it because it's super awesome. And so I would love, and I would not lose sleep over giving every single person that's in this class an A. There's no issue with that, but it's just that this is not what usually happens, okay? I hope you all get an A. I want you all to get an A, but it's just that I need to do my job properly. Does that make sense? Anyone have any questions about that? I'm happy to answer any questions.
So you're saying 85% above the A plus, or like it kind of might turn out to be that way?
Did you just miss everything that I just said?
No, it's like you know about like.
I'm kidding. Because that semester was particularly hard, because I had 3 tests, 8 homeworks, 15 quizzes, and 5 recitations in 6 weeks.
Okay, yeah, but you're just saying that, like, gauging how the course will go, you'll make your mind up. And
Yeah. So just if you just want a rough ballpark estimate, start at 90 A plus, and then 5% every third of the letter grade down. Yeah.
Does this mean there's no way to view your grade throughout the semester?
No, you can obviously ask me. So what I'm going to do on the course page is I'm going to actually list out in sorted order the scores earned by everyone in the class. So if you're at the top of the class, I wouldn't really worry about getting a high grade. But if you're at the bottom of the class and you're not usually there in your other classes, you may want to start working harder or understanding why you're missing points, okay? Yeah, so I will be as transparent as I possibly can. If you have any questions, just ask me. I'm happy to answer any questions you have. Okay, yeah.
Are there any bonus points?
What do you think? Well, the attendance is actually part of the class. There may possibly hint be bonus points on the exams. Okay. May possibly hint. Any other questions? Okay. So let's actually get into it. So how long has it been? So it's been 30 minutes. So let's go for 15 more minutes, take a break, and then continue on. Okay. Ready for the awesomest material you'll ever learn? I'm actually not kidding. Who's ready? Yay! Okay. So let me ask you a very precise question that has exactly one answer. You can tell by my sarcasm it's not. What is a computer?
Calculator.
It's a calculator. What else is it? Does it necessarily have to be a machine? And in fact, like the earliest computers didn't actually have any electronics or even metal for that matter. So what is a computer? Something that computes. Okay, that seems interesting. So something that computes. Well, computes what? Ah, inputs and outputs. Okay, well, what are typical inputs that a computer might have? Well, that's technically the right answer, but like generally, what types of inputs are you used to? Are you used to writing 0, 1, enter? So, how many of you read Far Side comics? Oh, you absolutely should. So there's this one-panel comic of a person at a computer, and it says real programmers code in binary, and there are these 3 buttons, 0, 1, enter. So real programmers code in binary. So, but really, what types of inputs do computers usually have?
Strings.
Yeah, strings, but do you work with strings or do you work with what things on the computer do you usually use?
Keyboard, mouse.
Yeah, keyboard and mouse, right. So you have these inputs, right? So you have all kinds of inputs. So like keyboard is an example. You might have a mouse. What other types of inputs might you get? So think less hardware type things. Although there are others, hardware ones.
Sound.
Yeah, I think sound would be a good one. What else?
Power.
What's that?
Power.
Power. But does that come as input usually to a computer? I guess it could, yeah. So power is another one. But can an input come over the network? Yeah, certainly. So anything to do with networking, or yeah, so anything to do with networking. Okay, so that's fine, unless someone is dying to add another one. Okay, so and so along with inputs come what? Outputs. Okay, great. So there are outputs over here. So we got inputs. What are some outputs that a computer might have? What is the obvious one that you use every single day?
Screen.
The screen, yeah. Screen, image, yeah, all that stuff. What other types of outputs might happen?
Sound.
Yeah, sound, to mirror the other sound one. What other outputs might we have?
Network.
Yeah, again, network also. What else could there be? You could have things sent to a printer. So it's not necessarily just literally on the computer things happen. It could be sent to another device near it, and then the output happens there. That could happen. Okay, so I think this is a pretty exhaustive list for most everyday things that might occur. So you notice I left a little space in between these two. So what do you think goes in that middle? So something that takes these inputs as input and produces these outputs. So does it really make sense for a computer to consume input and not give any output whatsoever? That seems kind of useless, right? Even if it's like written to a file, like the result of a computation written to a file, that is an output of the computation. So I can even put that also, so like file in here. So there's got to be something that converts from these inputs over here to these outputs over here. As junior level, I think, programmers, what do you think usually goes there? How do you take inputs to make outputs? So some type of function, or is more specifically what? What do you write? You're computer programmers. What do you write? Programs. Okay, great. So things that can go in here, so computer programs. Could a human be involved in this? Yeah, so it's not necessarily just computer programs or humans, but much more generally, what happens here? We're computing a function. So a function, remember from 243, takes inputs to some other domain, some output. So here we're really computing a function, or you can think of this as we're doing computation. So there's something that happens here that does this function somehow. It takes these inputs, does some processing, whatever that needs to do, and it produces outputs. Is that clear? Okay. So let's see. Well, could a computer or whatever this thing is, whatever this computational device is, could it have as many inputs as you want? Could it have 10 inputs and 10 outputs? In principle, could it have that? Yeah, I can just add a USB or several USB hubs and plug them all in, right? Do we really need 10 though? Or could we just get away with 1? So I'll actually show you a way that you can show that I don't need 10 inputs. I can just match them all up into one gigantic input and then to one gigantic output. So think of it this way. So let's just say that we have the keyboard having input values in binary, let's say 0, 1, 1, 0 stuff. Let's just do 3 to make it easy. And then the mouse is 1, 0, 1, 1 stuff. And then the sound is 0, 0, 1, 1 stuff. How can I merge these 3 inputs into one gigantic input? Here's what you do. So I'm going to switch colors. Anyone else like Notability? I like Notability. Good. So what I'm going to do is I'm going to take the first bit of the first input, the keyboard one, and I'm going to write it down here as 0. Then I'm going to switch colors again and go to the first bit of the second input. Okay? So the 1 right here. And I'm going to write a 1 here. Switch colors again. Let's say green. And then I'm going to do it like this. And then, so I wrote the first bit of each of the inputs down. Then I'm going to take the second bit of each of the inputs down. So like this. So 1 here. Then the 0 comes here. And then the second bit of the third input, second bit of the third input goes here. So what we're doing here is we're interleaving the inputs together. So if I wanted to know what the first bit of the sound input is, I just ask for the third bit in the input. Okay, so all we're really doing is we're just interleaving the inputs together. So do we really need 10 separate inputs, or can we get away with one? So I'm not saying whether this is practical or not. So this is actually the one class that's really nice that we can avoid any physical constraints of the universe. So we can just avoid any thing that sounds inefficient and just ask, can we do it at all? So can I do this at all? Yeah, so I can certainly do this. So no issue there. Okay, and then obviously this continues all the way down. So therefore we can say, oh, we only have one input. And so we only need to worry about one input here. Can I do the same thing with the outputs? We can interleave the outputs exactly the same way. So that's kind of cool. So we're going to consider a single input and a single output. So we're abstracting all of the details away. Again, a nice thing about this class, we abstract all the details away. So we're just looking at a single input, single output. Okay. But I'm actually going to make this even easier. You think, okay, this is really easy. This is really dumb. We're only at one input, one output. Ryan, you're going to actually make this easier? I'm actually going to almost eliminate the output entirely. And all I'm going to do is I'm going to have two possible values to output. So instead of outputting a whole binary string, we're just going to output a single bit only, a 0 or a 1. Okay? So either a 0 or a 1. Is this a lot easier now? I think that's pretty easy. So essentially all we're saying here is that we take an input and we say yes or no on that input. Pretty simple. So the reason why I'm making that simplification is that it's much, much easier to analyze this way. It's much easier. So this is the model that we're going to actually look at. Okay. Well, let's see. Well, when we do this computation here, are we going to actually just do the computation raw? Or are we going to have some registers or something to store data? So in a computer, do we have registers to store things like intermediate values? Yeah, so there's some places that we can store stuff. And even if we didn't have registers, do we have like a storage device that we can store things in? Yeah, so like main memory, and even if we didn't have main memory, God forbid, we have like secondary storage, like solid state, hard drive, whatever. So we have some places that we can store stuff. So, but let me ask you a question. Are computers deterministic? So like if I woke up my machine tomorrow with the exact same configuration, the same memory layout, same everything, and I did the same program, would it do the exact same thing? Yes. So computers are deterministic. Okay? Well, let's see. So if I take this input right here, so I should be able to expect a 0 or 1 every single time, the same output every single time because the computer is deterministic. Cool. Well, let's see. Let's extend that a little further. Suppose that instead of just waking up my machine, I wake this machine up in the middle of a computation. So I've already had a program going for, say, 6 weeks. And I freeze somehow my computer. And then a month later, I wake up my computer again in the exact same state. Literally the same memory layout as it was before. Would it continue doing exactly what it would have done? Yeah, because computers are deterministic. So for that reason, we can think of the memory layout as something that can be stored, or a state of the computer. So whatever the memory layout of my computer is, it's some layout of bits, but we can think of that as a single state of the computer. And if I wake up the computer in the exact same state, it'll do the exact same thing from that state no matter when I do it. Okay? So we can think of memory layout of computers to be states. Okay? So the memory layout of a computer is a state. How much time do I have? I have 5 minutes, okay. So memory layout of computers are states. Okay, so obviously what's going to happen is we have a state. So let's just say we're in a current state right now, some memory configuration, and we do one instruction of the computer, some kind of execution, one step. Am I going to get to some other state of the computer? Yeah, so if I change the value in a register, that's going to change some bits, or it might not actually change things, but something's going to happen, and the result of that is going to be a state. So what we need to do if we're going to analyze this is we got to look at states of our computer and relate them together somehow. There's some kind of relation between the states of a computer. Well, let's see. Let's just say that we have a particular state that we're looking at. Could it be that, let's just say that if we're in this state, we could output 1 right now. Say yes on this input. Let's just say that we are in one of those states. Could the computer carry on other computations after that point, even though we could say 1 or 0? Could the computer just carry on and then eventually say yes or no at some point later? Yeah. So some states we should mark as 1 states and some 0 states as other states. So what will happen is if we do our computation, end up in some memory configuration, some state, we have identified each of the states with either 0 or 1. We said this state is a 0 state, or this state is a 1 state, this state is a 0 state. And if we end up in that 1 state and the computation's all done, then we say 1 on that input, or yes on that input. If we end up in one of the 0 states, we say no on that input, or 0. So we gotta set each of the states to be 0 or 1 states. But there's something else we need to look at, if that isn't already enough. Well, when I start up my computer, does it start in the exact same state every single time? Yes. So I know, ignoring secondary storage. Think of just main memory here. So do we start up in the exact same start state every single time? Same memory configuration every single time we wake the computer? Yes, every single time. So we gotta identify one of the states to start with. So we gotta set one of the states to be a start state. So there's one state that is going to be labeled as a start state, and every state that we're going to look at is either going to be a no state or a yes state. Okay? I think that's long enough. Let's take a 5-minute break. Okay, let's get back into business. Everyone survived the first half of a lecture? Let's see if we can survive the second half. Okay, so if you haven't signed the attendance sheet, it's up here. You can sign at the end. Okay, so any questions on the first half? No questions, so everyone got it 100%, correct? So I see people taking photos of this. What if I told you that I will be giving all of these to you, all of them, for free? Okay? You can take photos. I don't really care about that. Okay, any questions, though? Okay, super. So let's actually look at one of these machines. And you'll think, okay, Ryan, this is super easy. Why are we even looking at this? So we got to start somewhere. We got to start at the most basic level possible, okay? So let's look at a two-state machine. Not billions of states, just two simple states, and that's it. So here's the machine that we're going to look at. And I'll explain all of the notation in gory detail in a second. And there is our humble machine. Machine numero uno. Okay, so what in the world is this machine? The circles here. So all of the circles, so Q0 and Q1, ignore the outer circle on Q1 for now. Just the circles, those are states. So each one of these, so these are states of the machine. So is Q0 a state? Yes, because it's encased in a circle. Is Q1 a state? Yes. So, okay, so that's fine. What are these arrow things between the states? So what are these arrow things? These are transitions. And then you may say, my watch thought I saw said, hey, Siri, okay? So it recorded everything I just said and tried to make a search off of that. All right. So you may think, okay, these transitions, I see one between Q0 and Q1. It has a certain label on it. And the other direction, it also has a label on it. You mentioned, Ryan, before that the transitions between the states on a computer correspond to executing an instruction, right? And I'm pretty sure, but I think 0 is not an instruction of a computer. Is 0 an instruction of a computer? A real instruction that you would run on your x86 processor. Is 0 an instruction? I mean, a bunch of zeros might be, but just a single 0. No. So what is the beauty of this class again? Abstracting the details. I don't care what the instruction is. I just simply don't care. If I see a 0 on the input, I'm going to execute that transition. So if I'm in the state Q0 at any point, and I see a 0 on the input, what state am I going to go to? Q1. If I'm in state Q1 and I see a 0 on the input, what state am I going to go to? Q0. I know it sounds tedious, but it's important. Okay? Does everyone understand the transitions between the states? I'll get to the other stuff in a second. Yeah?
Would it be incorrect to call the transitions input since it goes from one to another, or is that so?
You can call them inputs, yeah. I'm going to use the term transitions. So sometimes I'll use on input 0 from state Q0, we go to state Q1. Okay? So, but you can think of inputs, transitions, exactly the same. Because each of the transitions has a single character label on it. Any other questions about the transitions? So, what do you think this arrow is that's coming from nowhere going into Q0? What do you think that represents? The start state, right. So we gotta start in some state. And because computers are deterministic, we can't start in any number of states. We gotta start in exactly one state because computers are deterministic. So I picked Q0 to be the start state here. Can Q1 be the start state possibly? Could I arbitrarily just say, set that arrow to point to Q1 instead? Could I do that? Would it change the behavior of the machine, though? It might, but am I allowed to do it? That's the thing. I'm not getting an enthusiastic yes or no. Who votes yes? Could I do it? Who votes no that I can't do it? Okay, so it's mostly yes. All right. So I could set Q1 to be the start state, but I am setting Q0 to be the start state. And only in exactly one of these states will get this arrow thing. Okay, and then the final thing is, what does this double circle represent?
Accepted state?
Yeah, so accept state. So remember from before we said all of the states in our machine could be set to 0 states or no states, or they could be 1 states or accept states. So the double circle here means accept, or quotes yes. So if we end up in this state, then we say yes. Question for you. Because computers are deterministic, if I'm in Q1 and I still have input left, can I say yes right now? No, because computers have to do the exact same thing every time. If they see something on the input, they have to proceed because they're deterministic. Okay? So for that reason, if we've run out of input entirely and we're in Q1, can I now say yes? Yeah, because I've run out of input. So that's actually another thing that we're going to consider in our model. Let's just say that in your computer program, I provide you a string. Could you go back and forth across that string as much as you want? If I give you a string of characters? Could I set a for loop to go forwards and then another for loop after it to go backwards? Could I do that? Yeah. So what we're going to do in our model is to make things a lot easier. You can only go forward in the input and never go backward. So what happens as a result is, because we can only move forward, if we've consumed a character, is that character essentially never going to be seen again? Yeah. So we're only going to move forward through the input. It makes the analysis a lot easier. Okay? We're trying to make this as easy as possible. Okay? So we're only moving forward through the input. So let's actually model what happens on a particular input, because it'll motivate the formal discussion later. So what is a possible input to this machine? Could I provide the input 1, 1, 1 to this machine? No, why not? Oh, there's no transitions anywhere in the machine labeled 1 out of a state or something. So what are the possible inputs for this machine from any state? 0. Here's another thing. Suppose that our inputs could be a 0 or a 1. Could Q0 have a 0 transition but not have a 1 transition? Because computers are deterministic? No. So in fact, every state in the entire machine must have all possible outputs that they could conceivably have. But could a state, for example, have, say, Q0, have 2 outputs labeled 0? Could a deterministic machine have something like that? No, because now it has to make a choice, right? I don't know which one I'm going to actually do. Could a machine have a 0 on one transition and a 1 on another? Yeah. But could it have no transition labeled 2, for example? Am I allowed to have that? If the input could have a 2 in it? No. What if the first character is a 2? What do I do? It doesn't know what to do. So I have to provide for every single state everything that could possibly happen. We'll have ways of saying, this is an unwanted input. Do something with it. we'll have ways of dealing with that. But for now, we have to have every transition of every possible input present. Okay, so let's look at a particular input. So can someone give me an input, a valid input for this machine? 1010, is that a valid input for this machine? No, what is a valid input for this machine? 00. I'm actually going to put another one. It fits with my notes. Okay. Okay, so when I turn on the machine and I have not done any computation at all, I've just turned on the machine, what state am I in? Q0. Why? Because that's the labeled start state. Good. So I'm going to model what state I currently am in. So I'm in Q0 right now. I have not read any input. Are we good? I know it's tedious, but it'll make everything else easy. All right. So now I'm in Q0, and I have read one character. There's only a 0 here to consider. But what state am I in after reading that one character?
Q1.
Q1, because I just followed the transition labeled with that character, and then after I'm in Q1. Perfect. So now at this point, what state are we in? We're in Q1 right now. So do we have more input to read? Have we exhausted the input yet? No, we have not read all of the input yet. So what do? Help me along here. I keep going. So what do? What character do I read? The next 0. And what state do I end up in as a result?
Q0.
Q0 again. Cool. So we've exhausted that character. Are we done reading the input yet? No. So what do? We go back to Q1 after we consume that the next character. Are we done exhausting the input yet? Yes, we are. So did we land in an accept state or did we not?
Yes.
We did. So what do I say on input 000? We say yes on this input. So we say accept. If I can write accept. If I fed you the string 00, which has two zeros in it, what would you say on that input? No, or reject, or whatever your favorite word is. Here's another thing. Could I have said Q1's not an accept state, neither is Q0. Neither state is an accept state. Could I do that? No, I'm not asking whether it makes sense. Could I do it?
Yes.
Yeah, I could do it. It'd be a pretty dumb machine at that point. I'm wasting a state, but am I allowed to do it? Yeah. So I can have any subset of the states correspond to accept states. Okay? As long as it's a subset of the states, we're okay. Let's do a more complicated example. Or are there any questions about this example? Let's do a more complicated example with 4 states. And then 8 states, and then 16 states, and then you know what happens after that. So I'm going to have 4 states, zeros across on the top and on the bottom. And then 1s on the up and down between the 0 and 2, and then the 1 and 3 state. So I claim that this is a deterministic machine, where all the inputs could be a 0 or a 1 at any point. So this is something that unfortunately happens. A professor comes up and tells you something, and then you have to make the choice of whether you believe it or not. So this is something that is called proof by intimidation. So let me try not to intimidate you and not lead you down the garden path with this. So is this a deterministic machine?
Yes.
It's not me just telling you this. Is this in your opinion or your observation, is this a deterministic machine? Yeah, why?
It has all the inputs and outputs.
Well, let's see. Let's look at every state. Does it have a 0 leaving it and a different transition labeled with 1? Well, look at Q0. It has a 0 going across, 1 going down, 1 same idea, 2 same idea, 3 same idea. Okay, so that's good. What if the inputs of this machine could be 0, 1, and 2? Is this a deterministic machine?
No.
No. So it's important to set at the very beginning what are the valid inputs to the machine. Because one set of inputs could be valid and then the other one might not be. So if the set of inputs that could be here is 0 and 1, we're okay. No problem there. So let's see. Can anyone give me a string that is accepted by this machine? Any string at all? Yeah, 0 is 1. What's another one? 0, 1, 0 is good. So let's just make a list of some accepted states, strings. So 0 was accepted, 0, 1, 0 is also accepted. Just one, and we can make an infinitely long list, obviously. What about rejected strings?
0, 1.
0, 1's example. 1, 0. Let me write one for you. Ooh, what's that simple? Anyone happen to know? Epsilon. So yeah, so you're actually correct on that. It's actually the string with no characters. So let's look at the empty string here. So the empty string is the unique string without any characters in it. Okay? Well, is the empty string accepted by this machine? No. What state do we end up in after reading the empty string?
Q0.
Yeah, Q0. We don't go anywhere because we don't. Well, first off, there's no transition labeled epsilon here for reasons we'll get to. But more importantly, because the empty string has no length and going across a transition involves consuming a character, empty string has no characters, so we can't execute a transition. So therefore we are stuck in Q0 and therefore we are not accepted. Cool. Let's go back to this machine for a second. The 0, 0 machine up above. Can anyone give me an English description for what strings are accepted by that machine?
Odd number.
Yeah, odd number of zeros. Anyone disagree? Yeah, and we can actually prove by induction that it is. Well, the string of length 1 goes there, and every odd length above a certain number is because we can just do however many transitions we need to do, and then one more back, one more forward. And then the even length strings are not because we always end up at Q0. In fact, the name Q0 represents the modulo by 2, so the parity of the length of the string. So if we take a string of length 100 and modulo 2 that, what is 100 remainder 2? 0. And so therefore we end up at Q0. So the name actually is kind of helpful here. By the way, you may be wondering why states are named Q whatever. That's actually just purely tradition. I have no idea why they're called Qs, whatever. In fact, a better name would have been S something for states, but Q is just the name that was picked. What about the second machine? Anyone happen to know what that is? Yeah.
Odd number of zeros or odd number of ones.
Odd number of zeros or odd number of ones. I'll disprove that. Pick any string with an odd number of zeros and an odd number of ones. That has even length.
0.
Yeah, 0, 1, for example. And then we'll end up in Q3 as a result.
Sum of 0 and
So that's one formulation. So the number of zeros plus the number of ones is an odd number. That's another way to look at it. Yeah.
Odd number of zeros or odd number of ones, but not more.
So that's another formulation. Here's a much easier formulation. Odd length strings. But what is the difference between these two machines? What does the first one have that the second one has that the first one doesn't? It has ones on the transitions. So could we actually make this second machine simpler than the one that's here with 4 states? In fact, we can. So we can do something like this. And then that works. It's exactly the same set of strings. These two machines accept the same strings because they do the same thing. So you may be wondering, okay, Ryan, what is this comma right here? So this comma represents multiple transitions. So it's not the transition labeled 0, 1. It represents a transition labeled 0 and another transition also labeled that's labeled 1. And then the same idea in the back direction too. So these are 2 examples of this deterministic machine. Any questions on these? Cool. Is this formal? This picture right here, is that formal? So this Q0, Q1 one, or this 4-state one, or this 2-state one down here, could I present this to a computer and say, compute it on this string? Could I present that picture to that computer? What does it need? It needs a specification to say, here are the exact state names. Here are the characters that are allowed on the input. Here are the transitions. Here's the start state. Here are the final states, provided as lists or whatever. But it's provided in a formal way to the computer. And then the computer, upon receiving those 5 bits of information, goes, now I know what deterministic machine you're talking about. Okay? So do you think there's a reason why we should care about formalisms? Maybe you don't, but we'll get there. All right. So, but mainly the reason is that you could be talking about, so in fact, the interaction that we just had where a student just said an odd number of zeros or an odd number of ones, but I gave a counterexample. But the student probably thought an odd number of zeros exclusive or a number of ones. Is that the case? Say yes.
Yeah.
Okay. Yeah. So there's a problem here. English is extremely informal. So I could be saying something to you, and then hopefully you understand, but there could be some miscommunication here because you grew up in a different background than I may have. I may say things in a way that you might not understand. English is a terrible way of communicating formalisms. So we need a formal specification that is unambiguous here. So what do we want? We want a machine that's deterministic and has those 5 parts that I mentioned before. So let's get right into it then. So a deterministic finite, and I'll get to that in a second, automaton, or a DFA. So we're pretty much going to say this the rest of the class. If I'm going to say the acronym DFA, what does that correspond to? DFA. Deterministic Finite Automaton. Okay? We'll have a lot of 3-letter acronyms in this class, TLAs. So, anyone get that? It's late, I know. Okay, so a deterministic finite automaton is what? We need to specify 5 pieces of information: the states, the inputs to that machine, the transitions of that machine, whatever start state of that machine is, and whatever the final states are of that machine. So is a 5-tuple, and then we're going to have 5 names: Q, sigma, delta, Q0, and F. Where? So 5-tuple just means 5 pieces. That's essentially all it is. Where, and then we gotta specify various things on the 5 pieces. So let's see. I wrote finite here. First off, do you want to draw an infinitely sized DFA? We all have a finite amount of time, so we probably should work with finite machines, okay? But another reason is that if I allow you to use infinite sized machines, then that actually drastically changes the power of the model. So finite makes this a lot easier and is actually the right model to work with. So by that reasoning, should we allow you to have infinite number of states? No, we're only going to allow you to have a finite number of states. Any number that you wish, but some number of states. So Q is a finite set of states. Cool beans. What about, so Q is a finite set of states. Sigma is what? For each of the states, should I allow you to have infinite number of transitions out to other states? No, probably not, because then I have to actually take an infinite amount of time to figure out which transition I should apply. So sigma is a finite input alphabet. Should there be an output alphabet for this machine that we're talking about? Are we outputting strings here, or just going into final and non-final states?
Final, non-final states.
Yeah, non-final, non-final. So in fact, we don't need to output anything. So we actually don't have a output alphabet here. I'm actually going to skip over delta for now, and we'll come back to it, because it's the most complicated piece. What do you think Q0 is? It's the start state. Well, let's see. Should it be a member of Q, the set of states?
Yes.
Yeah, that seems intuitive, right? But we provide you a set of states. Let's just say I provide you Q0, Q1, Q2 as the set of states, and I tell you Q3 is the start state. Do you think there's something wrong there? Yeah, so then you'll think, okay, what machine are you trying to tell me? So it better be the case that Q0 is a member of Q, is the start state. And if I go over time, please stop. I won't take points off or whatever. Okay, what about F? What do you think F corresponds to? Just intuitively. The states that are final, right? Well, let's see. Could it be equal to all of the states? In other words, every single state is final? Could that be possible? Yeah, it could be possible. Could it be that none of the states are final at all? So 0 states are final?
Yes.
Yeah, that could be possible. But could it be any subset of the states at all? Yes. So it could be any subset at all of the states. So let's just let F be an arbitrary subset of Q. Is the set of final states. So I'm going to tell you set of states, input alphabet, whatever the start state is, a set of final states, and then we'll get to transition in a second. But any questions on these 4 pieces? Yeah.
When you say when we said the set of final states, don't we have to specify what the final state is gonna output? If it's gonna be, could we have a machine that has a final state that instead of accept something, it's gonna say no to the input?
So the determination we made is that all accept states are going to be yes states. They're going to say yes, and all things that are not accept states are going to say no. So there's a correspondence.
So the finals are always accept.
Yeah. So final is always accept. Yes. And if you're not accept, you're always non-accept. Yeah, non-final. Yeah. Other questions about these 4 parts? Because the 5th, the transition function is going to be a little bit wonky. So let's see. So delta, what does delta do? So let's look back at our example. So let's just look at this Q1 right here. So how did we determine that it was Q1? How did we figure that out?
Current state and input.
We looked at the current state. Okay, so what was the current state in this case? Q0. What was the input character that we looked at to get to Q1? 0, right. So we looked at the current state that we were in and the input character, whatever it is, and then what happened as a result? What did it give us back?
Future state.
The state that we're supposed to go to. Okay, so think about that. An state and an input character together is going to yield another state, or maybe the same state, but a state at the very least. Okay? Any questions on that? Okay, so let's see. Well, we can think of transitions as just a function that take us from what? We got to provide a state and an input character, and it yields from those 2 things the next state. Well, what is the set of states here? Q. So it takes things from Q, and what was the character from? What set was the character from? From sigma, the alphabet, right. So we're going to think of these as ordered tuples. So, and if that made absolutely no sense to you, what should you look up? Chapter 0. Okay? Okay, so we're thinking of these as ordered tuples. So we're thinking of them as just pairs. Think of ordered pairs. So the first element of the pair is a state, and the second one is the character. Well, what is the transition function output? What should it give us back? What? State. What are states from? Q. Should I bar any state from appearing in either one of the Q places here? Should, like, say, the start state not appear in any one place? No. I can have transitions from any state to any other state with any label I want. Okay? I'm not going to forbid you from saying transitions can't go back to the start state or whatever. I'm just going to allow you to do whatever you want with the transitions. Okay? Well, yeah, is the transition function? I'm not actually done here, but we're almost there. I promise. Well, let's see. It's a function, but does this guarantee that any state with any input character has a defined state to go to? And in other words, so think of like this example right up here. With the definition of the function, just a function as it is, could we have a situation like this where we have an undefined transition out of a state? Yes, we can. I'm not allowed to have 2 transitions with the same label going out. I'm not allowed to do that because it's a function. But could I have an undefined transition? Yes. So how do we actually specify that? To say in the formal part that there's no undefined transition, whatever that may mean. So delta, we're going to have an additional specification, is a total function. And I almost guarantee you no one's ever heard that term. Anyone heard that term? Total function? Unanimous. So what does total mean? All total means is no matter what state and symbol you provide, the next state is defined. So this total business will forbade this situation from happening. We can't have a transition on a symbol and an undefined transition on another one. This situation cannot possibly happen because delta is a total function. Total function means no undefined transition. Okay? But we needed some way to specify that there is no undefined transition here. Any questions on that? Okay. So let's actually write one of our machines formally. So I'm going to harness the power of notability again. Hopefully I can get this good. God, I love notability. It's so amazing. Paste. Ah, yes. Do you make sounds when you do your homework like this? Whoosh, whoosh. All right. So let's actually look at this machine. So is this picture formal? No. So let's make it formal. So if I want to specify this machine formally, how many pieces do I need to define? 5 pieces, because DFAs are defined with 5 pieces. So what is a simple piece that we can define right now? The states, for example. So Q, the set of states, is what set here? So remember, it's a set of states. Okay? So I better write that it's a set because it's a set of states. What is this set as elements? Q0 and Q1, because they're elements of this set. Super. Here's a great exam question. Hint, hint. Can a DFA have 0 states? We have 1 yes? No? Anyone got a maybe? One of the least favorite things about being an instructor is when you ask a question, you get a yes, maybe, and a no. It's amazing. I love it. So we got a yes and a no. What is the true answer? No. And why is it no?
It's a 5 tuple, so it has to have Q0.
Ah, it has to have this 4th piece right here. Q0 is an element of the set of states. So does the empty set have an element in it? No, because it's defined to have no element in it. So by saying that Q0 is an element of the set of states, could a DFA have 0 states? No. So all DFAs have at least 1 state. Could they have 1 state only? Yeah, we could have transitions that go back to the same state if we wanted to. Okay, let's go back to our example. What is the input alphabet in this case? The only character 0. Could I have defined it to have other stuff in addition? No. Ignoring the picture. Just ignore the picture. Could I add more characters if I wanted to? Yeah, so as long as it's any finite alphabet, we're good. Here's a great question. And there's actually a bit of disconnect between what Sipser says and what is actually mathematically true. Can sigma be empty, have no characters in it? I'll let you think about that. because it's actually a very interesting question. Whereas Q cannot be empty, but could sigma be empty? I'll let you think about it. But this one has 0 in it. So what is the start state in this machine? Well, it's Q0 because it has this incoming label to it. What is the set of final states here? Just Q1. So it's a set containing Q1 in it. So remember, Q, sigma, and F are all sets, all of them, all three. So if you're going to write them out, they better be sets. Okay? So now let's go on to the business of the transition function. So I'm going to show you a shortcut over just writing the transition function over and over and over. And it's actually using a transition table. And so what a transition table is to say each row corresponds to a state, and each column corresponds to that input, and the entry of a certain row and a certain column corresponds to coming from that state on that symbol. Okay, so what do I mean by that? So let's write a table here like this with 2 rows because there are 2 states, Q0 and Q1. And how many columns are there? In other words, how many symbols are there in the alphabet? Just 1. So there's 1 column. So 0. So what do I put in this box right here? It's going from Q0 on input 0. And what state is that one in this case? Q1. Perfect. And what does the other box have? Q0. And that's all 5 pieces. So we have completely determined formally what this machine actually does. Oh, by the way, when I said total function here, all that means is that the transition table has no holes in it. So there's nothing blank in the transition table. That's an equivalent way of doing that. But we've specified this machine formally. We've written the states, the input alphabet, what the start state is, what the final state in this case is, and what the transition table actually is. Any questions?
So that's it.
Yeah, class over. Any questions? That's the complete definition of a DFA. There are other definitions, but I'm not done. I have 5.5 minutes. I will use every class all the time. So let's actually get some other definitions out of the way. So let's just let sigma be an alphabet, if I can spell alphabet. Well, we could talk about all of the strings that you could ever generate over sigma. So maybe 0, 1 is our input alphabet. You can think of all binary strings, for example. So basically, all strings that have a 0 or 1 in them in any place. Okay? So if we want to talk about that, so we're going to let sigma with a star on top of it be all the strings over sigma. So an example of this would be 0, 1 star. That is all binary strings. Another example would be 0. So A, B, C, D, etc. I don't want to write them all out. Up to Z, star. So that's all alphabetic, I guess lowercase words. So we can talk about that all binary strings, for example, but in general, if we have a set, we can put a star on top, and then that's just all strings with elements in that set. So 0, 1, all strings with 0 or 1 in each place, and the other one is a letter in each place. Okay, so let's actually talk about how to actually compute something. So how did the DFA actually compute? So these are DFAs up here. Look at the string 0, 0, 0 from before. How did it compute that string? Or say yes on that string, I guess. How did it do that? Well, where did it have to start? What state? Start state, I hope. And then what happened at each point along the way? Well, we followed the transition with that character, right? So we looked at the first character and we said, oh, let's follow the transition labeled that. Then we arrive at a state. Then we looked at the next character, figured out where to go from there. Then we looked at the next state and figured out where to go from there. Well, let's see. How did we know that we were done again? Well, do we have to end at a final state? We used up all the input, right. So once we use all the input, we either end up at a final state or we don't, right? And then that last check will determine whether that string is part of the strings that the DFA says yes on. So let's make some more definitions. So a language is a subset of sigma star. So sigma star, remember, is the set of all strings you could ever generate over sigma, and a language is just a subset of that. That's all it is. Another way you can look at it is a language is a set of strings. So just a few last things. Can a language have infinitely many strings in it? Yeah, so think of all binary strings, for example. That has infinitely many strings in it. Can a string be infinitely long? No. So a string, remember from 243, I hope, is a finite sequence of characters. So all strings are finite, but a language could be infinite. Okay? So an example that we had before was all the strings in 0, 1 star such that the length of W is odd. And we saw that this can be recognized by a DFA. I'll define what the term recognized means next time, but because of the example, we could have a DFA accept exactly the strings in this language, the set of all strings that have odd length. Any last minute questions?
What was the answer to the question you asked?
Which one?
Can the set of strings be zero?
So the technical answer is yes. Sipser says no. So I'll see you all tomorrow.